Hello everybody. So in this video we continue with chapter 9, vectors, lines, and planes, specifically section 9.2, scalar or dot product. Let U be a vector with components u1, u2, and u3, and vector V with components v1, v2, and v3. The dot product or scalar is written as u times v and is defined as u1 times v1 plus u2 times v2 plus u3 times v3. In other words, we multiply the components and add them. And also we have that u times v, or the dot product of uv, is equal to the magnitude of u times the magnitude of v times the cosine of theta, where theta is the angle between the two vectors. So where does this come from? Well, notice that if we have something like this, if we have u squared, this is going to be u times u. And from the scalar product, we know that this is going to equal u1 times u1 plus u2 times u2 plus u3 times u3. And this is simply going to equal u1 squared plus u2 squared plus u3 squared. But if you look at this, this is the same as saying the magnitude of u squared. So what happens if we have the magnitude of u minus v squared? This is going to be the same as u minus v times u minus v. And from algebra, we know that this is the same as saying u squared plus v squared minus 2 times u times v. But from what we saw previously, this can also be written as u squared, or I should say the magnitude of u squared plus the magnitude of v squared minus 2 times u times v. So let's relate this now to the law of cosines. From the law of cosines, we know that the magnitude of u minus v squared is equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle theta, which is contained between u and v, as we can see in this triangle. Now, notice that this and this equation are equal to each other. So that means that this expression and this expression are equal to each other as well. Now, if we equal them, notice that we can cancel several things out. So if I rewrite this over here, magnitude of u squared plus magnitude of v squared minus 2 times u times v, we're going to cancel this out with this and this. And if we rearrange, we are going to get that u times v, or the dot product of u and v, is going to equal the magnitude of u times the magnitude of v times the cosine of theta. So now we're going to work on example 9.8. And it says, find the angle between the vectors u, and they give us the vector u, and the vector v. So we learned that the dot product of u times v is equal to the magnitude of u times the magnitude of v times the cosine of theta. So notice that if we rearrange this, we get that the cosine of theta is equal to the dot product of u times v divided by the product of their magnitudes. Now, this is also the same as saying the unit vector of u times the unit vector of v. But we're going to use this. So what is the dot product of u and v? We already learned what it is, right? So we have cosine of theta is equal to 1 times negative 3, that's going to be negative 3, plus negative 2 times 6, that's going to be negative 12, plus 2 times 2, which is going to be 4. And then we divide this by the magnitude of u, which is going to be the square root of 1 plus 4 plus 4, and this times the magnitude of v, which is the square root of 9 plus 36 plus 4. And then from here, we're going to get minus 11 over 21. So that means that the angle theta is going to equal the inverse cosine of this. And this is approximately 2.12 radians. If two vectors are perpendicular, then the dot product is 0. Why? Well, this is because if they're perpendicular, the angle between them is either plus or minus 90 degrees, and therefore, if we do the dot product in terms of cosine, then it would be the magnitude of u times the magnitude of v times the cosine of 90, which is 0. These are known as orthogonal. Now notice that the base vectors of the coordinate system are obviously perpendicular. If you do the dot product of I and j, then you're going to get 0, and the same for the other ones. Now, when the vectors are parallel, the angle between them is either 0 degrees or 180 degrees, and therefore we're going to get cosine of 0, which is 1. So in this case, the dot product is just going to be equal to the product of their magnitudes. Or if the angle between them is 180 degrees, then we're going to get that the dot product is negative the product of their magnitudes. We continue with example 9.9, and it says, determine which, if any, of these vectors are right angles to each other or orthogonal. So let's do the dot product first of all of u times v. So this is going to be 7 times negative 3 plus 3 times 5 plus 2 times 3. And this is going to give us 0. Therefore, these vectors are orthogonal. So let's do the dot product between u and w. This is going to be 7 times 1 plus 3 times 0 plus 2 times 1, and this equals 9. Therefore, not orthogonal. And finally, let's do v times w. And here we're going to get negative 3 times 1 plus 5 times 0 plus 3 times 1. And this is obviously 0. Therefore, these vectors are orthogonal. So now we have example 9.10, and it says the vertices of a triangle are A, 1, 2, 3, B, negative 3, 2, 4, and C, 1, negative 4, and 3. Show that the triangle is right-angled and find its area. Okay, so for this we need to find the vectors, right? So vector AB is going to equal minus 3 minus 1, this times I, plus 2 minus 2 times j plus 4 minus 3 times k. And this is going to give us minus 4i plus k. Then we have a vector AC, which is going to be 1 minus 1i plus minus 4 minus 2j plus 3 minus 3k, and this is going to be minus 6j. And then vector BC is going to be 1 minus 3, so 1 plus 3 for I. Then we're going to get minus 4 minus 2 for j plus 3 minus 4k. So this vector is going to be 4i minus 6j minus k. Okay, so notice that if we do the dot product of AB and AC, we are going to get 0. Notice AB times AC is going to be minus 4 times 0 plus 0 times negative 6 plus 1 times 0. And this is 0. Therefore, the vectors are perpendicular, so the right angle is going to be at A. We can see this in the drawing to the left, right here. So the area of a triangle is equal to 1/2 base times height. So in this case, we can say 1/2 the magnitude of AB times the magnitude of AC. And from here, we're going to get 1/2 times the square root of 16 plus 1 times 6. And this is going to give us that the area is equal to 3 square root of 17. So now we're going to talk about direction angles and direction cosines. Figure 9.19 shows a non-zero vector v, which we can see here. The angles alpha, beta, and gamma that the vector makes with the unit coordinate vectors are called the direction angles of v, and cosine of alpha, cosine of beta, and cosine of gamma are called the direction cosines. So let v equal xi plus yj plus zk. Considering that the right angled triangles OAP, OCP, and ODP, they all share the same hypotenuse, which is OP, or the magnitude of V. Now, the side adjacent to an angle theta in a right triangle is related to it by cosine of theta is equal to adjacent over hypotenuse. Therefore, the adjacent is equal to the hypotenuse times the cosine of the angle. So in this case, we can express x in terms of the magnitude of v times the cosine of alpha, y is the magnitude of v times the cosine of beta, and z is the magnitude of v times the cosine of gamma. So the vector itself can be expressed in terms of these expressions. So notice that vector v is now going to be v, magnitude v times cosine of alpha times I, plus magnitude of v times cosine of beta times j, plus magnitude of v times cosine of gamma times k, which can be summarized into this expression. Now, if we take the magnitude to both sides, we're going to get this, that the magnitude of v is equal to the magnitude of v times the square root of cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma. Now, this implies something. It implies that cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma is equal to 1. In other words, the sum of the squares of the direction cosines is always 1. And if we have a unit vector, that is, the magnitude is going to be 1, you're going to get that the vector is equal to this. In other words, the expression without the multiplication times the magnitude of the vector, because the magnitude of the vector is 1, like we just said. This means that for a unit vector, its x, y, and z coordinates are its direction cosines. Now, it is also important to remember that we can find cosine of alpha by dividing x by the magnitude of the vector. Cosine of beta would be y divided by the magnitude of the vector, and cosine of gamma is going to be z divided by the magnitude of the vector. So now we have example 9.11, and it says, find the direction cosines of the vector v, and it's 4i minus 2j plus 4k, and then approximate the direction angles to the nearest degree. Okay, so the first thing we need to do is find the magnitude of this vector. So that's going to be equal to the square root of 4 squared plus negative 2 squared plus 4 squared. And this is going to give us 6. So the unit vector is going to be vector v divided by the magnitude of v. So this is going to give us 2/3 I minus 1/3 j plus 2/3 k. So then from what we just learned, we know that cosine of alpha is going to be 2/3. Then cosine of beta is going to be minus 1/3. And cosine of gamma is going to be 2/3. Then that means that alpha is going to be approximately 48 degrees. Beta will be approximately 109 degrees. And then gamma will be approximately 48 degrees. So we continue with example 9.12. And it says, find the angle that a main diagonal of a cube with side A makes with the adjacent edges. We can place the cube in a coordinate system such that 3 of its adjacent edges lie on the coordinate axes as shown in figure 9.20. Now notice here that we can say that the diagonal is represented by the vector v, which has a terminal point A. This implies that the magnitude of vector v is equal to the square root of a squared plus a squared plus a squared, and this is obviously a times the square root of 3. And then if we take angle beta, which is an angle that the diagonal of the cube makes with one of the adjacent edges, we would say that beta is equal to the inverse cosine of the side A divided by A over square root of 3. And this is the same as the inverse cosine of 1 over square root of 3. And this gives us approximately 54.7 degrees. So we will finish this video by doing example 9.13. And it says, the point C is at the center of the rectangular box whose edges have measures A, B, and C. Find the size of angle ACB in terms of A, B, and C. So they want us to find the size of this angle here. Okay, so notice that the coordinates of this vertex over here are A, B, C, because A would be the distance in the x-axis, B would be the distance in the y-axis, and C is the distance in the z-axis. Now, because point C is at the center of the rectangular box, it means that its coordinates must be halfway to ABC. So that means that point C should be A halves, B halves, and C halves. Now, in order to solve this problem, we need to know what vector AC is and what vector BC is as well. So point A, right here, would have coordinates A, 0, 0. And then point B would have coordinates 0, B, 0. So that means that vector CA, so vector CA is going to be equal to A minus A halves, comma 0 minus B halves, and 0 minus C halves. And this is obviously going to be A halves minus B halves minus C halves. And then vector CB is going to be similar. It's going to be 0 minus A halves, B minus B halves, and 0 minus C halves. And this is going to give us negative A halves, b halves and negative c halves. So from the cosine rule that we learned, we know that the cosine of the angle ACB is going to equal the dot product of CA times CB. So it's going to be the dot product of these vectors divided by the magnitude or the multiplication of the magnitude of these vectors. So the magnitude of vector CA times the magnitude of vector CB. Okay, so we continue down here. This is going to equal A halves times negative A halves plus negative B halves times B halves plus negative C halves times negative C halves. And this over the magnitude of CA, which is going to be the square root of A squared over 4 plus B squared over 4 plus C squared over 4 times the magnitude of the other vector, which is going to be the same, right? So it's going to be A squared over 4 plus B squared over 4 plus C squared over 4. Okay, so notice that this is going to give us minus A squared over 4 minus B squared over 4 plus C squared over 4. And all of this over A squared over 4 plus B squared over 4 plus C squared over 4. And then from here we can rearrange and simplify, and we're going to get C squared minus A squared minus B squared divided by A squared plus B squared plus C squared. So the size of the angle ACB would be the inverse cosine of this expression that we found.